So I'm reasoning that in 2012 it's still too expensive to create and maintain integration points. So we have software running on all different kinds of devices, Raspberry Pi, mobile phones, data centers, laptops, everything. And it's still too difficult to change the way that things communicate. So it's pretty easy to change software. We have a sprint. Business requirements require us to change the way that something works, but when it comes to changing the way that it communicates, it's still inherently pretty complex. So I also contributed monitoring patches to the ZeroMQ framework, and I co-maintain C binding, as well as a Ruby extension for ZeroMQ as well. So our agenda for today is basically just to define what it is and what it's not, which a lot of folks get confused with. They look at message patterns, how we can use transport and devices to grow our network, and then eventually use it, look at building resilient systems, and then how to use this from Ruby. So the first problem is, what is wrong with socket.io, the way that the standard TCP sockets that we know and use quite a lot. So who have used written a network server before? Who released one? Keep your hands up. Released one? Who's still maintaining one? Right, so that's a pretty hard problem to solve. So there's a particular developer profile required to do these things right. The second one is data portability. So like error codes, options, etc. that change between different platforms and different operating systems. And fortunately, like from Ruby, it's not that big an issue because higher level languages try to take care of these things for us at the interpreter level. And the biggest one is data flexibility. So we only have two ways of communicating, either bidirectional communication or we can do unidirectional multicasting. And that's fairly limiting if you look at the way that we communicate, or organizations communicate. Yeah. So what is ZeroMQ then? So it's zero broker. There's no broker. Because there's no broker, there's nothing to administer. And it's very cheap to start using. It has a really simple API. It's very simple to use. So everybody that's done software programming is familiar with binding, connecting, sending and receiving. So there's nothing new here to learn. And also it's free, and it was designed for the financial services industry, so there's almost zero latency in most things. So what it's not a turnkey messaging solution. It's not like RabbitMQ. It's a completely different market. We can probably like a good comparison here is between Git and Subversion. So we could say ZeroMQ is like Git, it's completely decentralized. It allows you to build like small tools around it, whereas RabbitMQ would be like Subversion. You need to have the central repository to be able to commit to. However, so something interesting here is that there was a project underway last year where they tried to basically get ZeroMQ into the kernel, or the kernel, and VMware funded this project. It's called the Scalability Protocol, and the goal of that was to try and get ZeroMQ into router infrastructure as well, so being able to make interesting decisions with reducing bandwidth on the internet or in networks in general. So that's something interesting to keep in mind. I'll talk about it a bit more later. So another good way to look at this is instant messaging for applications. So it's not really like for enterprise use. It is the financial service industry, but for very specific use cases, it's not a particular technology that's going to solve all your problems. So it's basically the main market is for medium-sized developers or small products that start growing, for them to be able to create an elastic network of your different services that they may or may not need. So it's not a messaging server. It's not a message queue, it's a communication and concurrency library, and it can also be used for data fabric, for transferring like huge amount of data between different endpoints. So it's kind of a very different market than what we normally traditionally get in message queues. And what it's done here is just added like messaging semantics to byte streams going on the wire, and just get the API, everything's similar to what everyone else is already used to. So how did we get here? So as with all good things, it started with tequila. And yesterday in the RabbitMQ talk as well, so Mark and Sue Strick, the original lead developer, and Peter Hinchens, they were responsible for the development and design of AMQP 0.8. So they worked with Morgan Stanley and a bunch of other industry giants. And they went through a lot of pain, a couple of years of extreme pain to get this fixed. And basically then ZeroMQ kind of is everything that AMQP is not. And the really important difference there, as I mentioned, is kind of an abstraction of messages on top of byte streams. And the initial market was the financial service industry, so it was always there for trading. very low latency, but unfortunately, like they never actually contributed anything back to the community. So right now, it's maintained by iMatrix and a bunch of contributors. And you may also recognize the name Crossroads.io, which is a fork from the original project a couple of months ago. So because it's a library, basically what it's done here is expose a really simple API. So if you just focus on like 4 methods, bind, connect, send, and receive. So this API allows you to use a library to create bindings or extensions for other different languages. So there's about 30 of the most popular languages supported. So you can connect all of these languages, like just ZeroMQ socket, everything just works, talk to each other. Interesting fact, the airline binding was written by the Goldman Sachs programmer, Sergey Lenkov, that was arrested, so he had a pretty good contribution before the jail time. And in the wild these days, as I mentioned, it runs on a bunch of different devices, so it actually ships on Samsung Galaxy X3 as well. And right now, Spotify uses it for the music feeds, AT&T uses it for number crunching, NASA uses it in scientific computing as well. So what I mean in the scriptable socket, so noted earlier, when we get like, most people do adult development, we get stories coming in our backlog, and most of them is like for changing business requirements or adapting to the way the business is changing. And most of them don't actually have anything to do with changing the way things communicate. So software tends to diverge, but then what happens is what we're left with over time. It's like as software changes, the way that they used to communicate, the integration point stays the same. And what happens is everything then becomes like really brittle over time, and this is going to be like more or less the focus of this talk, and kind of like to show examples and give you tools on how to like address some of these problems or things that people actually don't really pay attention to or don't talk about so much. So how does it do this? You just added a simple API model on top of normal socket, so it's actually like, it looks like a normal TCP socket, but it has a lot of stuff around it. So it takes care of multiplexing for you. Again, the API, it supports multiple transports, so we can send messages in the same process, we can send between processes on the same box, we can send, of course, on the network as well. So one of the first things with this type of socket design is you can bind and connect to multiple endpoints at the same time. So if I have a client and I want to connect to 10 different instances of the same service, that's not a problem at all. So that means that if half of that infrastructure goes down, then my client basically has the ability to do round robin balancing, figure out which endpoints are dead and which ones not, so you kind of move reliability back up to the edges of your network. Another thing that's pretty crazy is you can bind and connect in any order. So you can actually have a client come up before your server's up, which is really useful if you're working operations and you need to make changes to production systems, because you then don't need to have a whole rollout plan and coordinate a bunch of stuff. You can just do what you need to do, and if you configure it properly to be resilient and to buffer messages in all the right places, then that will never be a problem again. So for today's talk, I'm just going to focus on 3 different simple patterns. The first one is the request reply, or kind of RPC, which we're all familiar with. The second one is PubSub, which is used for data distribution, and then push and pull for work distribution. So touching like kind of what we can do with this. So as I mentioned, there's a binding ecosystem around this whole thing. Binding meaning extensions to different languages, not in the sense of ZeroMQ binding. And so here we have a simple ventilator that could be any application. So let's assume for this example that that's a Rails application that's actually pushing out work somewhere. And this work is here in the middle. So this is just a combination of workers. So they will be like, get work from somewhere, do something with it, and then republish the results. So it's kind of like, you can compare it to a similar kind of rescue worker. And any of these workers can be in any language. So you can have this tier being in Scala, that top tier being in Ruby. If you want to do your results sync, you can do that in Java. And you can then collect things in Hadoop. So with the multi-connects, we want to have that system being resilient. So if we notice like, hey, our ventilator is, or we want to some redundancy in the top, we can bind and connect to multiple endpoints. So now we just add another ventilator and another result sync. And any of these workers, one worker can die, one result sync can die, and one ventilator can die, and everything just continues to work. So in terms of message structure as well, and this is something that I kind of want to hit home here, is usually when people talk about messaging and messages, it's always referred to as a job. But in ZeroMQ, it should be considered like in-flight messages, so it can be anything. You can send photos, you can send videos, you can send anything you want to, but it's not necessarily, if you can wrap your mind around getting a rid of the job concept, and it opens up a whole lot of different responsibilities or different possibilities. Sorry. So the format, there's no specific format, there's no contract, so you can use JSON, you can use protocol buffers, you can just send plain text, like anything you want to. There's also no security, it's up to you to decide if you want to implement security, you can do it in technology that is suitable for your organization. So delivery, one of the guarantees that I mentioned, you could atomic delivery guarantees. So that allows you, if I'm sending a 5 GB video, then you can do that as long as there's memory on the sender, memory on the receiver, and you have network bandwidth to do that, then by all means you can do it. And the guarantee that you have is you always get the whole video, or you don't get any of it, but no, you don't have to do like buffer parsing and kind of trying to figure things out. And of course, no persistence, so it's not a message queue in the traditional sense. And that's for various different reasons. So first one is being performance, and the other one is a single point of failure, which this framework is basically trying to avoid. So the first pattern, I'm just going to take a quick look at those three that I mentioned just now. So the request reply, client server, we're all familiar with this. So three different variations. The first one on your left is just one-to-one client-server connection. The second one is an example of a client connected to different service endpoints. So now that client is a resilient client. If any of those services would die, it'll still be able to communicate with the other one. And the third one is what I mentioned. You don't need to take care of multiplexing or use event loops or anything like that. But just if you run or spawn a particular service on Linux, it will use equal by default, and you'll be able to handle tens of thousands of connections for that particular socket just by saying socket.bind, and then off you go. So as I mentioned, it's the only topology that can actually go both ways. All of the other two are going to cover it. This is just downstream. So this is the only one that can go in the two different directions. So the pub/sub topology is for data distribution. So the one we're all familiar with, pretty simple pub/sub. We can also invert this. So this is an example useful for logging infrastructure, which is if you have different Rails applications that's emitting logging infrastructure on pub sockets, then you can have a log subscriber, which actually, like RSOS has a ZeroMQ module as well. So what it allows you to do is just use your RSOS log infrastructure as usual, and even when you need to tap into log infrastructure to do analysis or just kind of see what's happening, you just spawn a subsocket, subscribe to what RSOS log is exposing, get some data out, and then just disconnect, and everything just goes back to normal. So use cases here, it's useful for market data like financial industry, distributed game state from massive multiplayer games. And there's an interesting difference here. So the current 9.9 release, which all of the different language extensions support, is ZeroMQ 2.2. And in 2.2, the pub socket doesn't do anything intelligent. It just, any data it has, it'll just send it to all the subscribers. So there's some problems with this in larger networks where you had a lot of congestion, so the network will just get completely flooded if you have like 1,000 subscribers in the same network segment. So 3.2 changes this with something called subscription forwarding, which basically it passes, if a subsocket says, hey, I want to know anything about Apple, then we'll pass that subscription back upstream, and then the pub socket will start filtering. And of course that's friendly to multiple hops as well, so you can significantly reduce network traffic in a downstream topology. The third one, pipeline for work distribution. And this is similar to what I covered in that larger example earlier. It's just kind of something pushing out work. So this is no different than rescue, which you probably can consider being equal to the push socket, and you have a bunch of workers, which is the pull socket. And use cases for this, it's very good for variable processing. So whenever a pull socket's done doing something, then it will just, the other ones will just kind of like, when they're done, pick up new work. So it's good for video transcoding, image resizing, and it's really simple to just add in, when you have to add a new feature, you just add a new layer to it. So if you have an image pipeline and now you need to do optimizations before you do something else, just add an optimization pipeline so it's kind of transparent to the endpoints, where it starts and where it ends. So transport agnostic messaging. So what does this mean? So as I mentioned earlier, you can use three different transports: in process, where you can communicate between threads in the same process, or IPC, which is inter-process communication in the same box, and then TCP for communicating between networks. So imagine you want to prototype a simple service like a small box of topology, and you just want to see like kind of how it works. You don't want to call the operations team, you just want to test it out. Then a good way to do this is to use an in-process transport, create different thread per socket, do what you need to do. You can deploy that one process, very simple to retire if it didn't work. And then suppose that that product kind of proved itself to be viable, then you can move that out and say, well, okay, let's take these threads and move these threads into like sockets into processes. And now we just change the transport from in-proc to IPC. And then later on, we can also see, okay, so this is really, really useful service. And then you can move that onto like web scale. So you'll use TCP transport, you can just move it on the network, and at this point, you're not bound by anything. And likewise, when you notice that the service is not popular anymore, you can go back from TCP to IPC, back to proc, and then eventually just kill it if it doesn't work. Devices, and this is really core to growing out a network, but this is like small responsibilities that you introduce into a product or a service. And a good way to look at this is it's kind of lightweight or programmable switches, so it's no different than the router you have at your home connecting ISP to your internal network. And a simple example of this is, let's imagine that this is a business requirement for doing persistence. So all of the work being sent out from a publisher needs to be logged for whatever criteria. So the only thing that we do there is then we inject the device. So the device is just a subsocket, pub socket, and it'll write the data to disk and then eventually just republish everything to the subscriber. So to the publisher and to the subscribers at the bottom, it's all transparent. They don't really care about the device being injected in the middle. And how this looks in Ruby, just a little red part is really simple. It's a hot loop, receive message from the front-end socket, do stuff with it, and just resend it. So it's really a simple contract. And it keeps like your architecture having really small responsibilities, not to have these huge monolithic components spinning out all over the place as well. So use cases here, it can be for proxying between networks. If you have networks using different message formats, data formats, and you can use that for translation. We could use it for dedupe. So if you're having like, you do a large-scale web crawling or something, if you've seen a particular resource that you've crawled like a couple of seconds ago and you want to do the work again, you can just have a device that just the only job is just to dedupe and filter, or you can use it for persistence requirements as well. Now, something to remember here, and as I noted, that the behavior should always remain transparent at the edges. So the interjection principle states that every time we insert an intermediate node into the topology, it should never change the behavior at the endpoints. So as long as you stick to this rule, bad things don't happen. Another example of saving bandwidth. So let's assume that this setup here is a massive online multiplayer game with clients in different geographical areas. So let's say that each of these subscribers is a gaming client. It could be a mobile device, it could be a computer, it could be something else. And then if we could figure out that these two players on your left-hand side, they're in the same geographical region, which could be the same city, it could be the same state boundary, then we can insert a device on the edge of that network, and what would happen is we could significantly reduce network bandwidth, network traffic, coming from the original game server back down to those particular two clients. So the wide area network link there would just be like sending data down once instead of duplicate for the two clients. So the only way to build resilient systems is to have all of your external dependencies being asynchronous. So for messaging and ZeroMQ specifically, there's two things that could fail: connection management and message delivery. And that lives in a separate I/O thread, which I'll get back to shortly. So how do we get resiliency from ZeroMQ? The first one is atomic message delivery guarantees. So it'll always, most of the time, like try and do the right thing and try and retry on failure. We can do multi-bind and multi-connect, so we can connect to multiple services, multiple endpoints, and the unordered bind and connect, which is probably one of the most useful features from the operation side of things, which allows for really, really easy upgrades in a service-oriented architecture. Something else to keep in mind here is it's all nice if you can just keep sending stuff down the wire, but of course networks fail, components fail as well, so you can't have a completely unbound system. If, for example, something happens, our worker infrastructure starts locking up, then everything will start dogpiling back up in the ventilator, so that's a behavior that you don't really want. And likewise, if your sync gets flooded, then we'll have results backing up in the worker tier. So a way to do this is with setting watermarks. So watermarks basically like a socket saying, hey, all the data coming into me, I'm okay with having 1,000 messages being in my buffer. And the behavior here depends on the type of socket. So if we have like a publisher, so given that drives like from left to right, it will drive your applications. What happens is if it can't keep up, it will drop messages, meaning that at least some messages will get through, so at least some of your stack is busy doing something. Whereas if it was just like blocking, then all of the stuff's just stuck, which is not what we want. So back to the reliability thing. So I've worked for a trading company a while before as well, and I would state that 99% of deployments don't need enterprise reliability. So all banks, all security companies, all trading facilities use something called reconciliation at the end of trading day. So your account balance during the day may not necessarily reflect your current balance, but it may not be actual balance. So there's always some form of reconciliation, and it's always a cost and time trade-off in trying. You can build perfect systems, but it will be inherently quite expensive. And I guess the environment that all of us work in is mostly smaller scale products or trying to innovate and doing new things, which of course you don't want to be blocked by trying to do the perfect thing. So back, I guess, when message queues were really popular, or at least the first ones started coming out, all transactions were really costly. So you maybe had like 2 banks, and they talked to each other, and they sent like 4 messages a day, and each of those messages represented maybe €1 million, right? So and there may have been like AS400 boxes on either end, and you had like 20 ops people like managing this thing. And it never changed, because it's the same for like 30 years. So if you drop one of those messages, you have a big problem, because maybe 20% of the daily revenue is gone. Like these days though, transaction cost is negligible, so we can retry, you can keep sending things, we have really fast links. Topologies are much larger as well, so if you're building products, you want people to use it, you want people to integrate with it, APIs and whatnot, business development, that's the whole point. So, and you can run all of these things, you have 1,000 nodes, you can run it with 1 or 2 guys with Chef. So it's a very different ball game, and of course everything changes quite a bit as well as the business environment changes as well also. So the way that ZeroMQ addresses this is reliability as patterns. So there's a guide called zguide@zeromq.org, and there's a couple of them basically for specific use cases. And I'd also advocate here that like there is redundant systems. It's better like it's solved, it's a collective problem, it's not solved a particular component. So it doesn't mean that if you're using Postgres, then you have a completely resilient architecture, or you're not prone to failure in particular aspects. It's about the system as a whole, and what ZeroMQ kind of forces you to do is to think of that whole domain, and not necessarily just kind of have a narrow focus and fall back into I have this program infrastructure, or I have this message queue that's just going to like everything's going to be okay, and we're going to drop a message, etc. So something else that's happening with these patterns is it's being moved into libraries as well. So for example, the major DOMO pattern is being released as low major DOMO. So what happens there is it exposes like maybe 3 different things or four different API calls, and it allows you to spin up like a rescue-like infrastructure. And again, you can now build bindings against this library. So you can have a binding for Python, a binding for Ruby. Now people don't actually need to think about these patterns, so you don't need to understand them. You just install the binding for your language and start using it. And then you can have some aspects of, for example, full-scale program infrastructure available to you. So performance characteristics of ZeroMQ is extremely, it's optimized for low latency and very, very high throughput. So it's actually much faster than TCP/IP, and I'll explain why in a short while. So lab numbers, 16-byte payload, 10 gigabit/second Ethernet, 8 cores. You can get up to 6 million messages a second. Or in Ruby, well, we're limited by GC, we're limited by object allocation, and of course, the language itself is not really that fast. So we can do 200,000 messages a second, which is much faster, I guess, than what most people would require anyway. So just 2 things about the difference between latency and throughput. So latency is always measured per message. So if you have like messages on your socket backlog, and you have the one in the front sitting there for like 20 milliseconds, and you have one coming in the back, maybe like message number 100. Now, we can't say that this is the average latency of messages on this outbound queue. What we need to consider is that the one in the front has been waiting for 20 milliseconds. So whatever resource that has to go to, it's going to be delayed by network round trip plus 20 milliseconds. So the latency of that message is going to be much higher than the one coming in last. Throughput, however, we can measure, we can average, we can say the average throughput at the sender, average throughput at the receiver, or in this part of the network is X to Y. So some of the optimizations that ZeroMQ, well, so this whole section is probably good enough for like 2 full-blown talks, so I'm just going to cover on one thing that's applicable to Ruby, and that is what I mentioned, the separate I/O thread, which takes care of connection management and sending and receiving messages. So what that means is, whenever we say socket.send, it doesn't mean that now there's a network interaction. It just means that that data is getting queued on the I/O thread, and that allows us then to have a simple contract. So between the Ruby extension or Ruby binding and ZeroMQ, our contract for sending messages is basically getting a Ruby string and getting that string converted to a message and into the outbound pipe, and the I/O thread will then at the next tick come around and send that out, vice versa for receiving. So it's a really simple contract. It's nothing complicated to work with. You don't need to understand a bunch of things about transports to make it work. So it's a very good model for higher level languages. It works pretty well with the Java extension as well. So how do we get higher throughput than TCP, even if we built on top of it? So normally what servers would do is every time you say like send a message, it will try and even if they're coming at a constant rate, will send. Every time we send, we traverse the network stack. So we're going up through the whole thing, just out the stack, we're going to network card, out in, etc. So what ZeroMQ does is basically if there's 1,000 messages or 1 million messages, or there's 2 messages, it will just, everything that's available will get sent at the same time. And this is because of the wire protocol, so it's a frame protocol. So all of the messages, you could just kind of batch them together. And on the receiver side, it becomes a bit complicated though, because if you get notified that the socket has data to read, you now need to read all of the data, because it could be a batch message just being sent, or it could just be one being sent. But this allows it to basically be very suitable for things like replication, sending videos. It's used in some movie production studios as well. So I guess, yes, this is, I'm just going to spend a couple minutes on explaining how we can use it from Ruby. So I maintain one of the bindings called RVC ZeroMQ. There's 3, like, I guess, popular ones, and they all have similar APIs. They're all based on the ZeroMQ API, so that's the nice thing about the languages or the bindings as well, is they all follow the same API rules. So it's fairly similar. If you have 20 different extensions for the same language, they will wind up looking pretty much the same. So the first thing that we need to do, as I mentioned, it's a highly asynchronous system, right? So it's easy to spin up like a huge network, but we don't have any idea of what that state looks like at any given time. So we don't know what state a socket is in. Is one socket getting a message? Is one socket sending a message? Is one busy reconnecting? Has one disconnected? So it's a lot of different state being kept around. So what we want to do is, if it's easy to spin up a network, then we don't want to just kind of kill the process where it's not the right thing to do in a network or a distributed system. So we create a context, and the context basically keeps state of all of the different sockets. So if we tell a socket like, hey, shut down your connection, and the socket will say like, okay, so this outbound pipe, it still has messages left to send. What do you want to do with it? You want to send it? You want to receive it? You want to drop it? And then eventually it will notify, like, it's like, as I mentioned, it's an abstraction on top of TCP, so it'll then go back down the stack and say, hey, TCP socket, like, to arrange yourself and then take the error code depending on the platform, etc. So this is just really important to keep in mind. This is why the context is there. So if you're initializing a socket, here's an example of, as I mentioned, multi-transport earlier. So now the only thing this process does is subscribes to data being published from somewhere else, and subscribes, expresses interest in receiving data that references Apple. And it can receive them through 2 different protocols, 2 different transports. So it'll receive it from a network device, TCP transporter, and also receive it from another process in the same box. And what will happen here is, we don't care where the data is coming from. For the use case of processing the data, it can come from the other process, it can come from a network. And this is just really like interleave processing, and it just makes it really simple. We don't have a contract with where it comes from. We just know we express interest and we want to get that from there, and we treat it like all the same. So a simple example of using concurrency. So how to take that worker model, where we have the push socket spreading out the work and pull sockets doing work. How do we implement this in Ruby with threads? So this works concurrent in Ruby 1.9.7, even with green threads, Ruby NES, etc. So our push socket, that's going to live in our main application thread. It's just something saying, hey, here's work to do, push it out. And really important, the gray area, which is where all the communication between the sockets happen. That's the separate I/O thread. Like, we never see that. That's managed by ZeroMQ. And then our application threads, which will log in thread.new, and then we spawn a socket. So how the master or push socket basically looks like this. We spawn a new context, we create a new push socket, we bind it to in-process transport called work, and we spawn 3 workers. And our main loop for the master is just get work from somewhere. If we get exit message, die. Otherwise, take the work and distribute it to our workers. And then the worker or consumer thread spawns a pull socket, and again it goes through a hot loop. And every time that it receives a message, it'll do work. So this will load balance under different threads. If one thread takes 1 minute to process, one thread takes 30 seconds to process, it doesn't matter. If we need high throughput, just add more threads. And also notice that this is a concurrent system. It doesn't have any mutexes, no locking, nothing. We just use message passing semantics for concurrent processing. So who's used the work of Mongo 2? Heard of the project? Right, couple hands. So this is a really, really good example of ZeroMQ done right. And he was actually one of the first adopters of ZeroMQ in an open source project. So how this works, it's a multi-protocol web server, so it supports Flash socket, JSON, Flash JSON sockets, and it basically, it's kind of like the Unicorn web server, but it supports multiple backends. So because of the nature of having like this huge binding for ZeroMQ, you can have a web server that talks to Python backend, talks to Erlang backend, talks to Ruby backend, talks to Java backend, and it's all transparent to the front end. So you can have normal Rails process. It doesn't need to be like a ZeroMQ endpoint as well. So it's just really a good way of having like the single front end that knows how to do the right thing with HTTP transports and just fanning out to your backend. And you can, of course, that like multi-bind, multi-connect semantics. It applies to Mongo 2 talking to your backends as well. So they can die, they can come back up, and nothing gets disrupted either. So how this looks, so Mongo 2 implementation, it has only two sockets. It has a push socket and a sub socket. And then backend A, let's imagine backend A is Python process and backend B is a Ruby process. And notice, like, if you look at the top tier there, again, push and pull topology, which is work distribution. So that's the inbound requests getting distributed to the workers. And then when the response is available, it'll just publish a response, and of course Mongo 2 knows how to get that response, or how, like which backend response needs to go to which client. So it's kind of like it becomes a broker for HTTP clients versus anything else you want to run in the background. So a couple of best practices, the patterns, learn them. I covered like 3 basic ones. There's a few others also. When you try and build systems, even though you can bind and connect in any order, always, if it's a server side, like server-like endpoint, bind it. If it's a client connected, it just keeps things really simple for everyone else to work with. Respect the interjection principle. If you're adding devices into a network, then always ensure that you never change your behavior on the endpoints, and set watermarks as well. So don't leave your network being completely unbounded. And of course, highly recommend reading the Z guide. So personally, I've probably read it now during a couple of months, maybe 3 or 4 times, and I'm still learning a bunch of stuff every time I do it. It's really, really well written, like it's 220 pages. It's actually just went from manual format now to being a book being released. It's that good. So I'd highly recommend, even if you just want to know about the technology, maybe just pick a chapter, read up, and the future. So coming back to the scalability protocol, what I mentioned was actually funded by VMware. So the goal there is to get these sockets living in kernel space and not user space, which means that because a lot of devices already, or network routers already run Linux, that means that you can deploy like kernel infrastructure on those. And I guess like one of the biggest problems moving forward is going to be with network bandwidth and congestion. And the goal of this project was kind of a proof of concept. They got it to the point where it's working, but I guess it's probably not the right time in the market to try and push that into production or on the internet as a whole. But that's just something really interesting with data distribution and trying to solve the network congestion problem. And it's also available on mobile systems, Samsung Galaxy S3, Raspberry Pi runs it perfectly as well. So you can't, for example, have a whole broker. You can't run RabbitMQ on your phone. Well, maybe you could, but not as easily as something small like this. And monitoring support was added in 3.2 as well. So one of the things that it did really well is whenever there's like network problems, you never really know about it. So there's a large amount of deployments that actually are starting having problems right now. Not necessarily problems, but they don't know what's running where anymore. It just works so well. There's ZeroMQ infrastructure in some companies that's been up and running for 2 years. They can't really identify where it is, what it's doing, what it's working. So it's not a good place to be because that may not be true moving forward. So it's kind of, I guess, an interesting time where there's ecosystem for tooling developing around the ZeroMQ. So I guess I'm done. If there's any questions or if people want to sync up afterwards, but yeah, so I guess we have a few minutes, 5 minutes, 10 minutes.
ZeroMQ is a relatively young library, and I wonder why are there already 3 Ruby libraries for Ruby bindings? How they differ, and what do you think about?
Yeah, so there's 3. Yeah, so I answered the first one. The first binding release was a normal like MRI specific extension. So it worked on Ruby 1.8, Ruby 1.9. And then right now, I guess it's kind of diverged away from like a couple of releases behind. So some people still use it, but it didn't work on Rubinius, it didn't work on JRuby. And then the ZeroMQ API library, so it was there to be able to run on like all the different platforms. It supports JRuby, Rubinius, and MRI. And then my binding, so yeah, I got the question a lot. So it's basically, there's a C client called ZeroMQ, which is like a higher level abstraction. So it exposes things like frames and messages and being able to actually do things where you can do a more traditional message system. So you can have like headers, footers, you can have different types of body, so you can have like a more formal implementation. It also ships with Sugar, like an event loop. So what you can do, for example, in mine is you can have a Ruby IO object and a ZeroMQ socket in the same event loop. And so there's some infrastructure around that. And like my rationale with this binding was that if I'm going to wrap the official C client, which there's a couple of hundred people that use it, and that's like actively use it in some environments, it's a lot easier to try and align your binding with that moving forward than with changes in the framework. And of course, if I go out and develop features, then I'm responsible. And of course, open source, we don't always have time. Sometimes it's it can be spotty. So yeah, that was my reasoning for it. And does that answer your question?
Yeah, sure. One more thing. How does these Ruby bindings handle serialization of the objects? I'm going to send something. Is Marshall downfused or something?
So it'll just be like, by default, it sends strings. So you can use whatever you want. You can use JSON and just send the JSON payload, or you can use anything you want to. You can use Marshall as well. Marshall probably is a bit more tricky because if you're using it from various different Ruby versions, so maybe like an old 186 client and maybe something more recent, then it may be differences in serialization compatibility. But JSON, protocol buffers, anything you want to, you can read a raw file, send it down the wire. Of course, it will go to Ruby string, but it's not. Yeah.
Cool. Thanks.
All right. You're welcome. More questions?